Bismillahirrahmanirrahim. Another important building block in our FEM formulation is the B matrix. We encountered this in our introduction, and the B matrix actually links the strain vector with the nodal displacement vector. Now, in case of 1D problem, this takes the form epsilon is equal to BU. Now, this epsilon is just a number. We are only concerned with epsilon x. This is the only significant strain component. Now, recall that for 1D problem, the displacement is also just a number, not a vector, because we just have one component of displacement u. Now, how we calculated the B matrix in that case was like this. We started with the definition epsilon x. This is the general definition for epsilon x, but in the case of 1D problems, it simply takes the form d over dx. Now, we know the value of u, that is nu d over dx multiplied with the nodal displacement vector. Now, putting in the values d over dx, two shape functions ni and j. This is just a review, and you have two displacement values, one at each node of the element. Now, dni over dx and dnj over dx. This gives us the strain for the element. Now, recall that we know the values of ni and nj, so just putting in those values, we have for ni we have xj minus x over l, and for nj we have x minus xi over l, and then we have the nodal displacements. So this gives us minus 1 over l and 1 over l, simple differentiation with respect to x. We have ui or and uj. Now this is epsilon x, and sometimes we can also write it like this. It's the same thing. Now this matrix, because it links the strain value with the nodal displacement values, this is the B matrix for 1D case. Now you recall this, we have done this earlier, so this was just a review, but using the same idea, we can now explore the B matrices for 2D, 3D cases as well. Now let's take up a 2D simplex element. And for 2D element, we have a triangle, 3 nodes, simplex element called I, J, K nodes, and these are the coordinate directions. Now in this case, epsilon is a vector, not just a number, because we have 3 components of strain: epsilon x, epsilon y, and gamma xy. Now, because we have already stated that the B matrix is a matrix that links epsilon vector with the nodal displacements, and recall that we have in this case 6 nodal displacements: ui, vi, uj, vj, uk, and vk. Let's show them on our diagram here. This is ui, vi, uj, Vj and uk v. So for each element we have 6 components of displacement and we have 3 components of strain. So this is 3 into 1 and this is 6 into 1. So we must have a matrix here of the size 3 into 6. That would be our B matrix. So let's see how we figure the components of that matrix out. Let's start with the first entry, epsilon x. Now epsilon x, in this case, partial u over partial x. Now for 2D problems, recall from the lecture on shape functions, our u is ni, nj, nk, ui, uj, uk. This is our u value. This is the interpolation function with these n's being the shape functions. Now, putting the values in the expression above, epsilon x will be partial ni over partial x, partial nj over partial x, and partial nk over partial x, ui, uj, and uk. This is the value of epsilon x. Now, when we put this in our empty matrix above, we realize that this relation for epsilon x has nothing to do with v values, vi, vj, vk, but here we have vi value, vj value, and vk value. So we need to do it like this. Partial ni over partial x, then there's a 0 here. The 0 multiplies with vi as it should because epsilon x is independent of v's. Similarly, nj over partial x, again 0. This multiplies with vj, and then we have nk over partial x, and again 0, which then multiplies with vk. So we have this expression shifted to our empty matrix above. So what about epsilon y? Epsilon y again, from its definition, partial v over partial. Recall the value of the expression for v for a simplex element. Again, it is very similar to the above one, nj, nk, nj, nk. Now this time this is vi, vj, and vk. This is the interpolation function. Now, putting these values here and taking the derivative with respect to y this time, we get nj over partial y, nk partial y, and then we have the displacement values, vertical displacement components. In a similar manner to the first row of the B matrix, now we'll substitute these values in the second row because we are talking about epsilon y now. Now in this case, because the expression for epsilon y is independent of u's, we have to put zeros here, here, and here, and then we have to put partial ni over partial y, partial nj over partial y, partial nk over partial y. Now, what about epsilon xy? Epsilon xy, from the definition, is partial u over partial y plus partial v over partial x. Now, the values of u and v are given here. This is u, this is v. So if we put these values in this expression and take the derivative, we should get partial ni over partial y partial nj over partial y partial nk over partial y ui uj uk plus partial ni over partial x partial nj over partial x and partial nk over partial x, and this time we have vi, vj and vk. Now here we don't need to put in our matrix zeros anywhere because ui, uj, uk and then vi, vj, vk are all here. All we need to do is put them in their proper places in the matrix above. So in this case we put the values like this: partial ni over partial y, and because this multiplies with ui, and then we move on to partial ni over partial x because this gets multiplied by vi. Similarly, partial nj over partial y and then partial nj over partial x, then partial nk over partial y and partial nk over partial x. So this is our B matrix because it links the nodal displacement values with the epsilon vector. Now this can be simplified further because we know the values of ni, ng and nk, so we can differentiate them with respect to x and y. So recall that the shape functions could be summarized as n beta is a beta plus b beta x plus c beta y over 2a, and this beta takes the form I, j and k. So this means that ni is equal to ai plus bix plus ciy over 2a, and j is equal to aj plus bjx plus cjy over 2a, and nk is equal to ak plus bkx plus cky over 2a. Now it is very clear that whenever we take partial derivative of ni, ng or nk with respect to x, we should only get bi because we should only get bi over 2a. And whenever we take partial derivatives of ni, ng, nk with respect to y, we should only get ci, cj and ck divided by 2a. So we can then, in our expression, we can, instead of these partial derivatives, we can just write the solution, and that is ni over partial x, so we'll only get bi over 2a, and because 2a is in every expression that we are going to get, we can take it outside, so we can write it bi. Then we have 0, then in the next we should get bj, then we get 0, bk 0. Next line 0. Now this is with respect to y, so here we have ci 0, cj 0, ck. Now here we have partial derivatives of x and y, but in the reverse order. So here we have ci bi, cj bj, ck bk, and here obviously we get the nodal displacements in the correct order. So this is the final shape of our P matrix, which for simplex element consists of constants only. bi, ci's are all constants divided by 2a, and compare this with the expression for 1D problem. You have again constants -1 and 1 and divided by length, here divided by 2. Now what about the B matrix for a 3D element, 3D simplex element? By similar considerations as in the 2D case, it can be shown that the B matrix takes the following form. Obviously, in this case, in the case of 3D simplex element, strain vector will be 6 into 1, epsilon x, epsilon y, epsilon z, gamma xy, gamma yz, and gamma zx. We have a 6 into 1 vector. So this is 6 into 1. On the right hand side, we should expect 12 into 1. That means that the B matrix must be of a size 6 into 12, considering that the displacement vector, the nodal displacement vector this time should be ui, vi, wi, uj, vj, wj, uk, vk, wk, and ul, vl, wl. So what are the values that the B matrix should take? It can easily be shown, like we did for a 2D case, that this takes the form 1 over 6v. We have bi 0 0, bj 0 0, bk 0 0, bl 0 0. In the next row we have 0 ci 0 0, cj 0 0, ck 0 0, cl 0. Next we have 0 0 ti, 0 0 dj, 0 0 dk, 0 0 dl. For shear strains, ci, bi 0, cj, bj 0, ck, bk 0, cl, bl 0. Then we have 0 pi ci, 0 bj cj, 0 dk ck, 0 bl cl. Finally, di 0 bi, bj 0 bj, dk 0 bk, and dl 0 b. So this is the final shape for the B matrix for a 3D simplex element. Now notice that in the 1D matrix you have length in the denominator. In the 2D case we have 2a in the denominator, and in the 3D case we have 6v in the denominator. The first one was a line element, the second was area element, so we have area, and the third one is volume element or solid element, so we have volume. Now all these bi, ci, di, they are all constants, and this is always the case when we are dealing with simplex elements.